Let's consider the contour integral shown. This is not a contour integral at all, actually. I wish to make it into one. Currently, this is just a real integral from 0 to pi of d theta over 1 minus 2r cosine theta plus r squared. You can actually do this integral through elementary means using the half tangent substitution, and I strongly urge you to try this using the half tangent substitution. You will get the answer. So this does not have to be done with any fancy techniques, but it's an instructive exercise to also do this using complex analysis. So how do you make this real integral into a complex one? What we can do is, recognizing that z equals e to the I theta, will make this into a contour integral where the integrand goes around a circle. So we'll write z equals e to the I theta, that's a unit circle in the complex plane, then dz equals I e to the I theta d theta. Let me take a moment to plot this circle in the complex plane. That's the real axis, that's the imaginary axis, and we plot this circle z equals e to the I theta. It's got magnitude 1, and the angle theta tracks its progress. Now observe that this intersects the imaginary and real axes at I, minus 1, negative I, and plus 1. Also, notice that if r is between 0 and 1, then r will be somewhere here. It's a real number also. And 1 over r, because r is less than 1, will be bigger than 1. So the 1 over r will lie there. This remark will be relevant in what comes below. So now we are ready to convert this integral into a complex integral. Cosine can be written in terms of complex numbers, because observe that z, thanks to Euler's formula, is also cosine theta plus I sine theta, and z bar, the complex conjugate, is cosine theta minus I sine theta. So what I can do is write this as z plus z bar over 2. By the way, notice that this is e to the I theta and z bar is just e to the minus I theta. So really z bar is just 1 over z in this particular instance. Therefore, I have cosine theta is just equal to 1/2 of z plus z bar, or z plus 1 over z, since we have just seen that z bar is the same as 1 over z. So we have cosine theta entirely in terms of z. Also d theta can be expressed in terms of z also. D theta is going to be, I can write this as negative I by transferring the I to the other side, because I squared is minus 1. Another way to think about it is I can multiply both sides by I, and that gives me minus 1, which I can transfer to the other side, divided by e to the I theta, which is z, dz. So now I have all the variables written in terms of z, and I have a legitimate contour integral coming up. Now what I'll do is I'll focus on integrating over the entire circle, even though the original integral only goes from 0 to pi. I'll tell you how to fix the answer at the end. Let's go over the entire circle, which I'll call C. And we'll go over the entire circle and write all the variables in terms of z. So that's minus I over z dz divided by 1 minus r times z plus 1 over z plus r squared Okay, all I've done here is substitute for d theta and substitute for cosine theta. And I'll call this integral I. Okay, now I can take the minus I outside and multiply the z throughout the denominator. So I end up getting dz divided by z minus r times z squared plus 1. Because that's z times z, which is z squared, and that's z times 1 over z, which is 1, plus r squared z. Now that's actually a factorable expression. You can verify this for yourself, but this will end up being I over r, the integral dz over z minus r times z minus 1 over r. So first you take a r outside and then you can factorize it like this. That's actually a very interesting situation, and that's why I had this r inside and 1 over r outside, because I'm going to end up with simple poles. The function f of z that we are interested in now is analytic everywhere except at the simple poles. The pole that is outside does not concern us, because the residue theorem of Cauchy just talks about the pole that's inside the domain of the circle in the interior of C. So only r, z equals r, belongs to the interior of C. And so that's the only residue we'll be worried about in the residue theorem of Cauchy. By the residue theorem, the value of this integral is equal to 2 pi I times the residue at r. Now that also has to be multiplied by what's up front, so that's I over r. So the integral I is just that. Now, by the various results of residue theorem, all we have to do of computing residues, all we have to do is multiply this throughout by z minus r. So the residue at r is just going to be the limit as z goes to r of f of z times z minus r. That's what you do for a simple pole, and here it is a simple pole. So let's compute this. If I multiply f of z, which is this, by z minus r, I end up losing the z minus r factor, and I just have the limit as z goes to r of 1 over z minus 1 over r. So the answer is just 1 over r minus 1 over r. And so that's going to be r divided by r squared minus 1. Well, all of that is just the residue part. So let's compute the integral, which would be the product of the residue and everything else here. The integral I equals I squared, notice, is minus 1, so that's going to be negative 2 pi over r times the residue, which is r divided by r squared minus 1. A factor of r cancels out, and I can absorb the minus sign by interchanging the denominator's order, which is just as well, because r is less than 1. You would need 1 minus r squared so as to make this whole integral positive. Now this is an integral that goes from, the original integral goes from 0 to pi. Okay, this one goes from 0 to 2 pi. So we have to take half of it. So the original integral will end up being pi divided by 1 minus r squared. Like I said, this is not a complicated integral. You can in fact do this integral using the half tangent substitution, and I very much encourage you to do that. It'll tie up all the nice methods that you learned in this course, and you'll end up getting this exact same answer that you got with complex analysis.